So this class, we're going to be looking at the similar thing to make sure you get a better understanding of it. So remember, I told you that if you want the limit of a function, if you want the limit of the function, you want to show that the limit is equal to, let's say, L, as x tends to whatever. Most of the time I'm using infinity or x tends to something. The limit of a sequence, beg pardon. We're doing sequences. The limit, what did I use for sequence? AN? I don't remember any. What symbol did I use? Does anybody remember? Blue? Let me find it back. Remember my notes. I didn't remember, but
Sorry, it was 1 over n?
oh man, I was talking about general thing that I use. Because I want to explain the proof again. Explain what it is that you need to prove. So I'm looking for what I gave you. I'm looking for the definition that I gave you. Because I have different symbols sometimes, but I want to know which one I used. Okay, so the limit. Where is it? Oh, xn. Okay. Limit of xn equal L. Yeah. As n tend to infinity. As n gets large, the limit is going to L. Now, in the proof, you are supposed to show that as n gets large enough, no, I need to remember this as well. What number did I use, or what symbol did I use inside here after the minus? I want to be consistent, so that you don't get confused. So back in your notes, if you wrote anything, back after the minus.
What should it be? L?
Repeat that.
Should it be capital L? Shouldn't be xn
Oh,
minus
I forgot to use L. Okay, I used L. I forgot the L is up there. Because I know there, in my notes, I have X sometimes I have L, sometimes I have what I'd use again. Different letter, I don't remember what it was. I think it was B. I don't remember why I used B. Maybe it's going to that boundary. I don't remember. Anyway, since I used L, yes, I use L. I have to use L because L is what is right here. Thank you, Anthony. All right. Now, what we want to show is that as the n gets large, these two, xn and xl, are going so close to each other that L will be the limit that is tending towards. So it keeps getting closer and closer. We don't want to show, we don't care about what happens when it gets to the exact L. Of course, it can't get to infinity. So you see that it's going towards the L. So you want to make this epsilon as small as you can. So as epsilon gets smaller and smaller, in other words, as a distance xn and sorry, as n gets large enough, then the distance between xn and L is very, very small, which is what the epsilon is right here. So the absolute value, so epsilon is positive. The difference, of course, has to be positive because the absolute value is positive. But as n gets sufficiently large, you are supposed to be able to find a value m that as n gets larger and larger than that m, and that specific m value, then the distance between xn and L will be less than epsilon. So you want to prove that no matter what m you choose, no matter what epsilon you choose, no matter how small you make epsilon, there is an m that n is getting larger than to make that distance between these two smaller than epsilon. That's what you're proving. You're proving that no matter how small you make epsilon, there is an arbitrary m, which is large, that m is going to be greater than, that will make the distance between x and L smaller than that epsilon. So epsilon is the arbitrary number. You can pick any epsilon. You need to find an m that satisfies that. So when you're proving it, as long as you can find m, then you're good to go. If you look in the proof, it says for every epsilon greater than 0, there exists an m. So you need to show that there is an m. That's the part, that's the proof. Once you can show that there's an n that satisfies that. And you were saying something?
If you have that, if you should sketch a graph,
Mm.
epsilon, limit, xn, and so forth, where would m be located on the graph?
All right.
Or
Glad you asked. Let's do one. Oops. All right, that's supposed to be an arrow. Oh, I can't fix it up. Arrowish. All right. Let us put some things on it now. So let's say I'm putting the limit first. I'm gonna do it second, but oh crap. Pencil. Change the pencil. Just an L, and that's an L right there. So go across. So the L is right here. So now, if you have you are making the distance between, you're decreasing this epsilon value right here. Smaller you make epsilon, there's a different color for each of them. So you have distance. Then you have this distance here, use green. Let's say this is, you are chosen some epsilon, call it x plus epsilon 2. Oh, sorry, should be minus. The one down here should be minus. You have x plus epsilon up here. 1 x plus epsilon 1 minus. I keep writing plus. So these are epsilon 1, epsilon 1. 2. Oh boy. 2. Okay. So I'm just using two epsilons, like say you have x minus epsilon, x plus epsilon. The distance is larger. You get a small epsilon, x plus epsilon 2, x minus epsilon 2. You limit the distance, it's getting closer and closer to the limit as x gets closer and closer to a value on the x-axis. No, sorry, that should have been L. Out of mercy. You know what? It's L on the y-axis, x on the x-axis. Oh boy. See, that's why I say I need to be consistent. I must put one of them this time. It's done gone bad.
and wouldn't you like sketch some kind of graph of a function or any?
Sequence. We're talking about sequences, but yeah. So remember last class I showed you, like you have different values of x as when n is 1, a value down here, for example. When n is 2, there's the next value up here. When n is 3, there's the next value here from the limit, from the sequence. The sequence is getting closer and closer to the L. So that's what I want to show. There's a line right here. So as n gets larger and larger, remember this is a sequence graph. I mean, these are the x values here, and on this graph is xn, the values from the sequence. So I was saying, as n gets larger and larger, these are the n values down here. As n gets larger and larger, the values for the sequence are getting closer and closer to L. So what I'm saying is, you must always show that there is a specific m that you can find each time, and that m will be located on the, I call it the x-axis down here. As n, remember, the sequence as n gets larger, you can be able to find there exists an n, which is on the x-axis down here, that is larger than or equal to this m value, which is located on the n-axis. That will give a result up here, which is within that boundary between the, I go back the whole graph and put back the same thing. This is supposed to be L. I'm used to using X. That is within that boundary between L plus epsilon and L minus epsilon. That's why it's written like this. X n minus L is within that boundary right here. When you expand it, you're going to get L plus epsilon, L minus epsilon. So there is a sufficient large M, and that M is located on this axis. So this is where M would be, on the N axis, Anthony. Because remember, as N gets larger, there's a specific N, which N is larger than, which causes it to fall within the boundary between L plus epsilon and minus epsilon. No matter how small you make that epsilon, you can find an M that satisfies that. If it's last class, we're going to prove that there was a specific M that satisfies any epsilon. What you need to do now is show that no matter what the epsilon that you choose, you can find a number that would make it fall within that range, in that epsilon range. So what the proof is to show that no matter what epsilon you choose, no matter how small you make the epsilon, you can find an M that satisfies it. That's why it is proven that the limit exists. All right, so I'm now going to show you an example again. I think I showed you, I don't know how many examples I showed last class. So I want to make sure you understand that what you're proving. You're proving that there is an M that satisfies any epsilon that you choose. That makes you show that it is getting closer and closer to that limit. So you're going to see the values going closer and closer in here towards the limit. It keeps going closer and closer. The distance between the limit and the functional value gets closer and closer to L. I want to show that there's an M that satisfies that boundary, that makes the sequence fall within that boundary between x plus epsilon, L plus epsilon, and L minus epsilon. All right, so let's do another one. So we're going to prove that the sequence, let me clear this thing here. Prove, I can't remember the right words. Prove that the sequence n over n plus 1. I don't understand the words. I mean, right, to prove that a limit as n tends to infinity of this thing is equal to, let me see, we can figure it out. What do you think that's equal to? As n gets larger and larger, what do you think that's going towards? You can actually look at it and figure it out.
1.
1, correct? Because the 1 is going to become insignificant. Like 9 over 10 is 0.9. 1 over 2 is 0.5. So by the time you get to 999 over 1000, you see it's 0.999. It's getting closer to 1. They want to prove that this is true. So this is our sequence here. This is our xn. I think I circled a while ago. That is the xn. So xn is equal to n over n plus 1. Right? I want to prove that for all epsilon greater than, for all positive epsilon greater than 0, you can show that there is an n that makes this thing less than that epsilon. So what I need to do is do some little rough work first to find that particular m, and then we use it in the proof. That's what I'm going to go through now.
Are you saying N or M? I'm not sure which one I'm hearing.
M.
As in
Well, I said,
Nancy or M as in mango?
the thing you need to find is mango. That's what you want to find.
Okay.
There exists a mango that will make this expression over here true. The thing is that the proof is a kind of roundabout proof. You use the definition first to find the m, then backwards and sort it out in the proof. So the first thing you're going to do is find n, and then I'm going to show you what the proof looks like. The two things you need to do: find the m, then use them to prove it. So we need to find that m now. So first we start off by using definition. All right, remember, I underlined a while ago, this is what we're going to be using in both the proof. Well, we're going to prove that, but use it first to find the n. That's what I mean. So now we're going to find the n by using that. So the sequence is n over n plus 1 minus, what is the limit? 1. So we're going to simplify it now because I want to find a particular mango m. And that is going to be n itself. You're going to have to solve for n. That will be your n. All right. So here we go. So n plus 1, n over n plus 1 minus 1 is the same as n over n plus 1 minus, write 1 as n plus 1 over n plus 1. Subtract it. So n minus n is 0, minus 1 is negative 1 over n plus 1. Well, that is going to be, the absolute value of that is just 1 over n plus 1. Which we know, all right, let me write it down here. Continue it. 1 over n plus 1. Which one is bigger? 1 over n plus 1 or 1 over n? Which number do you think will be bigger? Remember that the n values are natural numbers.
1 over n.
But 1 over n is bigger. So that means that 1 over n plus 1 is less than 1 over n. Remember from the start, you know, this whole absolute value thing right here, that was less than epsilon. So if 1 over n plus 1 is less than 1 over n, sorry, if 1 over n plus 1 is less than epsilon, and it is less than 1 over n, we can just, okay, use the 1 over n, so that is less than epsilon as well. Because we know it's less than that, so all we need to do is show that 1 over n is less than epsilon. I'll make sure you understand what I'm saying. Since we want n over n plus 1 plus minus 1 to be less than epsilon, we want that to be the case. And we already showed that this is equal to 1 over n plus 1. And 1 over n plus 1 is less than 1 over n. Then once you show that 1 over n is less than epsilon, then 1 over n plus 1 must be less than epsilon as well. So anyway, so far we have this now. 1 over n plus 1 is less than epsilon. That's all we wanted to get to. So we can use that now to find a particular n. I'm using n as in never. But that n that we're going to solve for right now is going to be your mango, or m. Probably should use two different letters, you know. You can understand first. I'm going to underline it. We're going to use this n, which is less 1 over n, which is less than epsilon, to find a particular m mango to use in our proof. So all we have to do right there is solve for n. So since 1 over n is less than epsilon, multiply both sides by n and then divide by epsilon, we're going to get 1 over epsilon is less than n. That n is our m. So we're going to be using the n, the mango, sorry, as 1 over epsilon. That's what we just solved for a while ago. Once you get the n on the one side and the stuff, the expression with epsilon on the other side, that is the n that you'll be using for the proof. So we have found the particular n that we're going to use now, which is 1 over epsilon. All right? Now we're going to show our proof. So n, or m, beg pardon, as in mango, must be greater than 1 for epsilon for the proof to work. So you're going to do this all the time. You're going to use the actual scratch work. You're not going to, that's not the proof, you know. That is just finding the m. Once you have found that m now, we're going to use the m in the proof. So your first job each time is to find the m and use that m in the proof. So here we go now. Yes, Anthony.
All right. At what point did we discover that the 1 over n will be less than epsilon? I'm not
From the beginning.
gathering that. From the beginning.
Maybe it's because I didn't write it. All right. Maybe it's the way I wrote it.
Okay,
Yeah, we can do it in a sequence now.
n minus l is the same thing as the 1 over n plus 1, right?
Yes.
Where did we end up thinking that 1 over n would be less than epsilon itself? I know 1 over n plus 1 is less than 1 over n.
Yeah.
I'm not seeing where 1 over n would be less than epsilon.
Oh, that's what you're saying. That's what you're saying. Because you, all along we were working, I had this 1 over n plus 1 less than epsilon. But you see me using 1 over n now.
Right.
That's what you're saying?
Yeah, like as in why 1 over n is less than epsilon. I just want to know how is it? I
You
know
chose
1
it
over
to be
n
because.
plus,
Yeah, continue. No, 1 over n plus
you know
1.
that over 1 over n plus 1 is less than n. We also know that 1 over n plus 1 is less than 1 over n.
Right.
I don't see how we could conclude that it's 1 over n is also less than epsilon.
We choose that because when you're doing these proofs, you try to use the simplest thing that we can get, because we know that 1 over n plus 1 is less than 1 over n. We can just say, okay, make 1 over n less than epsilon instead of using 1 over n plus 1, because you get a more complicated epsilon if you had used the 1 over n plus 1.
Okay. So there's okay. I was looking for some computation.
No. The competition was actually knowing that 1 over n plus 1 is less than 1 over n.
Right.
Yeah.
Okay. All right. Okay.
Normally, when you have the fraction one, they try to get it to 1 over n if you can, instead of using 1 over n plus whatever is there, or minus whatever is there.
The idea is that 1 over n plus 1 is very close to 1 over n.
Correct.
So we're just concluding that it's likely less than epsilon. Because it's that close to 1 over 1 n plus 1.
That and simplicity. Because we know that 1 over n is bigger than 1 over n plus 1. So if 1 over n is less than epsilon, then 1 over n plus 1 must be less than epsilon as well. We just use that one instead because it's simpler than 1 over n plus 1. For the purpose of using it. Say that again. You say non-response. All right.
Yeah.
1 over n is simpler to use than 1 over n plus 1. And since you know that 1 over n plus 1 is less than 1 over n, and if 1 over n is less than epsilon, then 1 over n plus 1 must be less than epsilon as well. With the 1 over n instead of the 1 over n plus 1.
Okay. Well, I hear the logics you're using there, but we just assume that 1 over n is less than epsilon.
Let it be less than epsilon.
Repeat what you just said.
Remember, this is the rough work, this is not a proof.
Okay.
You can't just let something be less than something in a proof. But this is the scratch work or the rough work to get to the m. And know that we have an m we can actually use in the actual proof. So you see, because this is rough work, we can do anything we want to do in it, as long as it is not going against the information that we have.
Okay.
You follow me?
Yeah.
So when you're doing the rough work part, it's if, for example, if somebody had proceeded to use 1 over n plus 1 less than epsilon and they solve for n right there, they wouldn't lose marks for that. So if 3 of you did the regular 1 over n plus 1 and you solve from that and then use it in the proof, and one of you did this one, then the one person get bonus. So you don't want to lose marks.
I'm still stuck on the idea that 1 over n is less than 1. I'm not seeing the logics behind that. There's nothing there that suggests 1 over n should be less than epsilon.
What suggests that 1 over n plus 1 should be less than epsilon?
Because we look at x sub n is less than epsilon from the beginning. That x n minus l is the
We
same
don't know
thing
it to be
as
true, that's why we're proving it. We don't know it to be true yet, I find in the m you have not proven that n plus 1 minus 1 is less than epsilon. You haven't proven this thing that I underline right here. You have not proven that yet. We're finding the m that will make it true. Because by working this thing out right here, we haven't even shown that 1 over n plus 1 is less than epsilon.
okay, but we do know that n x sub n minus l, absolute value of that is less than epsilon, right?
We don't know that. That's what we want to prove.
I graph
See,
graph and we assume that to be true that particular formula is accurate, and so we can also show by any particular function that we get, or series in this case that we get, we can show it using that method.
but when you say x over xn minus l, you're talking about n over n plus 1 minus 1? Or are you talking about
Yeah.
generally? Xn minus
I
l?
say generally, the understanding would
No,
be that
generally, that is what it's not that xn minus l less than epsilon thing, is not a formula. It's something that must be shown to be true in order for the limit to exist and be the limit.
okay.
What I'm going to say is that we know it is true. We don't know it is true. That's what they want to prove to be true. So currently, when I wrote that thing, n over n plus 1 minus 1 is less than epsilon. We don't know nothing about it being true or not yet. We're going to prove it now by finding the m. Using m, I can prove sure it is true. I'm just asking these questions now because no one know that you aren't so sure about that part yet.
Okay. So we're saying that we don't know if 1 over n is less than epsilon.
Right, we don't know that yet. We don't know none of the things down here. By choosing that m, we're going to see if it is true or not, if it works. At that m,
Okay.
we satisfy make it less than epsilon all the time.
Okay.
All right. Let me show you something right here. N plus 1. If I had a whiteboard, I would have worked it out like this. And I said, okay, n over n plus 1 minus, it was like a space a while ago. Let me do it like that. And you work it out, this gives you negative 1 over n plus 1. That's an epsilon, which is 1 over n plus 1. That's an epsilon. But since 1 over n plus 1 is less than 1 over n, all right, now this to be true, make that less than epsilon then. So we can just work with 1 over n less than epsilon instead. Because since 1 over n plus 1 is less than 1 over n, if 1 over n is less than epsilon, then 1 over n plus 1 must be less than epsilon as well. Now just solve for the n right there. Which
Okay.
gave us 1 over epsilon. There. So we're going to use m as a greater than 1 over epsilon.
I got it now. It was an assumption. It's an assumption that is being made that 1 over n is less than epsilon. Once you make that assumption,
Correct.
it must mean that 1 over n plus 1 is less than epsilon.
Here you go. So we're going to assume, as I said, that 1 over n is less than epsilon. And if 1 over n is less than epsilon, then 1 over n plus 1 must be less than epsilon as well.
Okay.
So
once we can prove that 1 over n is less than epsilon, we can logically say that 1 over n plus 1
plus 1
is less than epsilon.
is less than epsilon as well. Correct.
Okay. All right.
All right, so for our proof, we're going to use this. Now, here's how you would write the proof. So, remember, to prove that, I'm going to go back and read the definition I gave you. To prove that a sequence converges to a particle limit L, then you need to show that for every epsilon greater than 0, and I mean you're from the proof now, there exists a particular m such that for all n greater than or equal to that m, xn minus L is less than epsilon. So that again, I'm reading directly from the proof I gave you. A sequence is said to converge to a number L. L inside the back there. So value. A sequence is said to a particular L. If for every epsilon greater than 0, that means positive epsilon, there exists an m, this big M right here. I'm going to turn it a bit backwards now, such that for every n greater than or equal to m, this is true. All right. So we have chosen our m to be greater than or equal to 1 over epsilon. Let's see if that particular m satisfies that thing that I just underlined. Let me underline it again. Let's see if that particular n satisfies this. All right, I'm going to erase the board now. Unless you're writing. I don't think you are. This was, I just wrote the thing I had before, but this time I wrote a little different. Let's ask, anybody writing? No. All right. So I'm going to prove that a limit exists now.
Sir,
Right, not
let me just write up a part for the epsilon.
Go ahead, go ahead, go ahead.
Zero.
You don't tell me what you're writing. Just write it and let me know when you finish. Because the thing that's most important now is you understanding what you need to do each time. So the sequence is, or the process is, solve for the m, use the m.
Okay, I'm continue, sir.
All right. You're looking for where's the text? There it is. All right. Where was I? All right. So we're going to know. Oh, we're going to use the m. So we had used m greater than epsilon. One over epsilon. So here's how we go to the proof now. All right. So the proof is that for every epsilon greater than 0, so start with that. Let epsilon be greater than 0. So epsilon is every number greater than 0. So we're going to choose m, capital M, to be greater than 1 over epsilon. Interesting, right? For every n, for every m greater than m, let's do it now. N over n plus 1 minus 1 is equal to n over n plus 1 minus n plus 1 over n plus 1. We're going to, this is, so what I started with now, I've started with the sequence minus L in absolute value. The same thing I wanted to show is less than epsilon. Is equal to negative 1 over n plus 1, which is equal to 1 over n plus 1. I took it out to absolute value, which we know is less than 1 over n. This is just now. Everything I've written so far is just, so on the left I did some algebra. I'm not bad at writing. But we know that it's equal to 1 plus n at the end, which for every number in the world that's positive, 1 over n plus 1 is less than 1 over n. Right, so now we're going to finish the proof. It's not finished yet. So I want to show that everything that I've written to the left, this, that, and that, we should show that it's less than epsilon. Once that's less than epsilon, we have done our proof. All right. Since n is greater than n, how do we know that? Sorry, m. Since n is greater than m, we say it right here. I want to prove that for every n is greater than m. So we know that n is greater than m. Good. But what did we say m is? What did we choose m to be from the start? The capital M. What do we choose it to be?
Capital M. What's the question again?
What did we choose capital M to be? What did we choose M to be? What did we choose mango to be?
Choose it to be N.
No, man, we choose it from the beginning, right? That's how you write the word choose.
I mean, greater than 1 over epsilon.
All right, we are choosing M to be greater than 1 over epsilon. All right, so since N is greater than M, which we had chosen to be greater than 1 over epsilon, then, let me know. N is greater than 1 over epsilon. Okay, yeah, that makes sense. That makes sense. Multiply both sides by epsilon. Epsilon times n is greater than 1, which means that epsilon is greater than 1 over n. Oh, so 1 over n is less than epsilon. Okay. Less than epsilon. So you have proven that if m is greater than 1 over epsilon right here, then n over n plus 1 minus 1 is less than epsilon. Look through that and see if you understand. I did as simple as I could. I'm waiting for questions if there are any. If there are no questions, that means you understand.
Just a moment and digest it a little bit.
Alright.
Sir, just bear in mind that this one is rough. Really rough.
You mean the topic?
Yes, sir. When they test us on it, don't go too hard.
So Anthony's digesting. Anybody digested yet and want to ask anything? Wake up to sleep no more. When I look in textbooks, they always leave out this first part. They don't show you how they get the M. Like mango. They don't show. You just see the M pop up. You say, how they get that? So I'm showing you how to get it, which I'll be testing you for. I'm testing to show you. Let me see how you get the M as well, because I'll make sure you know what you're doing. And that part is not hard. You just use the actual thing that you want to prove, go back with your M, and you go backwards and prove that. What you have shown, is that for every M greater than 1 over epsilon, that's the number that N is going to be greater than all the time, as N gets greater than that number. And the sequence is always going to be between L minus epsilon, L plus epsilon, which in this case is 1 minus epsilon, 1 plus epsilon. You guys finish writing, because I want to show you the next one if you don't have any questions. You can get used to them. The more you see, more you
Finish
get
right,
used to it.
sir.
You say you finished?
Yes, sir.
Alright, Jeremy. Anthony Lafferin finished? Nikila was here.
I understand. So
Good. Lafferin? Finish right?
digest. But go ahead.
Alright. I should not say anything, so I mean to finish. Alright, so let's do another one. So I'm going to prove that this limit as well, limit as n tends to infinity, so as n gets larger, the sequence is growing, squared plus n, so is equal to 1. Right, that's over. I'm trying to write it small to make it whole on the board. Just write big and done. So the limit has n to infinity, n squared plus 1 over n squared plus n is equal to 1. Sorry. So we want to prove that n squared plus 1 over n squared plus n minus 1 is less than n epsilon that we choose, as long as epsilon is greater than 0. So if I make epsilon 0.00000000001, it will work. It doesn't matter. I should use the one with ln. Oh well, whatever. I can do that one next if I have time. It's too fast. Well, not too fast, but fast enough. Alright, so let's start with that thing. We want to find a particular mango, m. So n squared plus 1 over n squared plus n minus 1 is equal to n squared plus 1 over n squared plus n minus n squared plus 1 Writing too fast. Over n squared plus 1. I'm just writing the, I mean n. Writing the denominator over itself. Get 1. So if you subtract that top part there, n squared cancel, we get 1 minus n. 1 minus n. So n squared plus 1 minus n squared plus 1 plus n. I know it's minus the whole thing, so you're going to get minus n over n squared plus n. Right, so we have that so far. Now, if we take the absolute value of that, that's actually the same thing as n minus 1 over. Oh, this is where it gets a little technical, because we want to get to a simpler thing as we can to prove, So we know that this is equal to this. N minus 1. Remember, n is going to be getting very large. I want to make sure it keeps it positive. N squared plus n. So let's think about that. That makes sense so far. Remember, n is getting larger and larger, tending to infinity. So to make it to keep it positive, we take the absolute value of it when it turns around. So like, for example, it was 1 minus 10 over whatever is down the bottom down there. It's going to be a negative number over a positive number. So to make it stay positive, we flip it around. Just let me know if that makes sense. All right. There's a no response. That means yes. Good. So let me write this back down here now. So n minus 1 over n squared. Why is squared not working yet? N is going to be now less than or equal to, follow me, n over n squared plus n. Well, this was not any.
All right, sir. Just a quick mention. In the previous step, the 1 minus, and if you had factor negative 1, negative 1 open bracket minus 1, then when you find the absolute value of negative 1, you just have remaining 1 times n minus 1.
Yeah, you could have done that too. All right, so back to the line now that I just wrote. N minus 1 over n squared plus 1 less than or equal to n over n squared plus 1. Make sense? We agree that is true?
Sir, or you get it to be less than or equal to, and not just less than. Or why is it less than or equal to?
Yeah, sorry. Why is it less than or equal to?
Yes, sir.
N minus 1 over. You could put less than.
Okay.
But you see, well, we just want to account for every number possible. Because like if n was a negative number, then it could be greater than it. But since we already said that n is a positive number, you're right. It's always going to be less than it. For all positive numbers, it's less than it. So you are correct in that regard. All right. So, well, I'm glad that the fact that you're asking about that means you understand that it is true. Because if numerator is bigger, then the number is actually bigger. So now that we can
No,
factor
sir.
out.
Because I asked means I understand that it's true. I just recognize it deviate from what the examples they did before.
Oh, that's
That's
what
why
you
I
asked. For example, we did before, there are different fractions and different rational numbers, so we can use the same. Sometimes it's equal, sometimes it's not.
Okay.
Okay, but that's what you said. So if you had used less than, it's the same thing, not to worry. Now that n over n squared plus 1 is the same thing as 1 over what? This time around equals, so you must be able to figure out what that's equal to. It's equal to 1 over what? Come on, people, you know what it is. That's
N
simple
plus 1.
algebra. N plus 1. Let's divide everything by n. Simplify the fraction, you know. Which we want to make less than 1. You guys must remember that now. Jermaine, since you like to use previous example, what's that less than? Or anybody?
1 over n, sir.
1 over n. You always try to simplify it as much as possible before you can put anything. That 1 over n now is less than epsilon. And if you solve it again, you're going to get m. I won't bother go through that, multiply both sides by whatever. You can do that already. M is going to be greater than 1 over epsilon. Went through the process before, cross multiply, whatever. Divide by epsilon, multiply by n, you're going to get 1. N is greater than 1 over epsilon. That's what we're going to choose as our m again. Now, the tough part, in my opinion, is finding that m, because you have to go through a little simplification, and sometimes to get what you want, you throw away some other stuff to get it to be simpler. You try to simplify it as much as possible while keeping it true. But I would simplify it and throw away stuff and then everything change, Simplify it but keep it true. Anyway, so we have now found our m. We're going to now use that m in our proof. So this is rough work, as I said before, which I want to see in the paper. But you make sure you write it as, call it rough work or preamble, or call it something. I think Americans call it scratch work. I don't know why I call it scratch. We call it rough. Anyway, that is our m. We're going to use it formally now in our proof. All right. Is anyone writing? 5.
No, sir. I'm sure.
No? All right. Fern, are you here? I haven't heard you all morning. Are you here? Fern?
Yes.
Oh, you're here. Okay. All right. Oh, sorry. I forgot the first part because you need to write this each time. Let epsilon greater than 0. Or some people say given epsilon is greater than 0. I just like to say let. So let be a positive number greater than 0. I generally want to make it as small as possible, as long as it is greater than 0. So it could be 0.0000000000000 10,000 zeros and then 1. It should be an m that we can find. Or we should be able to find an m. So let epsilon be greater than 0 and choose a comma. Choose m to be greater than 1 over epsilon. So you see, no matter what epsilon you choose, use an m. So for example, if epsilon is 10, then m is greater than, sorry, that's a 0.10, I mean 0.1. If epsilon is 0.1, then m is greater than 10. So we're going to use 11, 12, 15, quarter. If epsilon is 0.3001, then m is greater than 10,000. So there's always an m to satisfy it. That's what we're finding. We're proving that no matter what epsilon you get, you can find an m. That's the whole purpose of the proof. Anyway, so let epsilon be greater than 0. We're going to choose m to be greater than 1 over epsilon. All right, so let's go through. Then, for any n greater than or equal to that m, we get this now. N squared plus 1 over n squared plus n minus 1 is equal to n squared plus 1 over n squared plus n minus n squared plus n over n squared plus n. Just skip some of these steps and since it's already. Okay. When we're actually doing the formal proof, it's like we never did the first part, so it will take time. N squared plus 1 minus n squared plus n is going to be 1 minus n over n squared plus n. It's an n, look like a h. N Make it worse now. Stop fixing stuff. Which is equal to n minus 1 over n squared plus n. We know that because n is a large number, so it's bigger than 1. So the absolute value will be like that, or as Anthony said, if you factor out negative 1, you can do it that way if you want. You get the same thing there. Now, n minus 1, I'm just writing it again because we're going to a different line, not because I'm starting anything new. That is less than n over n squared plus n, which is equal to 1 over n plus 1, dividing top and bottom by n. And that we're going to know, we know is less than 1 over n. So let me go down here now and do this part again. N is greater than m. What? How we know that? That is part of the proof. For any n greater than or equal to m, but we had chosen m from once again to be greater than 1 over epsilon. So it means that n must be greater than 1 over epsilon. Which if you multiply and divide, whatever you're going to get, epsilon is greater than 1 over n. Which if you want to turn it around means that 1 over n is less than epsilon. By the n that we chose, which means that this thing is less than epsilon. So once n is bigger than 1 over epsilon, that's what we chose. That is the number that we can use all the time to get our proof that n plus n squared plus 1 over n squared plus n minus 1 is always going to be less than epsilon once you use that n value. So there is an n that satisfies it. Many n's as a matter of fact, as long as it's bigger than 1 over epsilon. You can find many numbers in the world that satisfy it. Hope it's getting a bit clearer now. So repetition, they say something about repetition, I don't know what it is. How much time I have left? 12 minutes. I want to start another one. Maybe if you write quickly, then I can probably finish quickly, yeah. Anthony, you should know that saying, what they say about repetition. I don't remember what it is. There's a certain saying about repetition and something with math. Jeremy, you should know it too. You only teach a profession business.
What's that, sir?
It's something about repetition. They say repetition
Deepens impression.
What's that?
Yes, sir. And I was just
Really
saying to
remember.
myself that looking at it the third time now, you start to see some stuff look like it starts to make little sense now.
Yes, man. Yes, man. First time it'll be frightening. There's some topics I learned in math for the first time. I was like, what? Teacher, move on to the next topic, sir. I don't know why they do it. I can't give a topic with less than 3 examples. It has to be 3 or more. Let me know when you finish writing, you know. Jeremy and Anthony probably. You finished? Okay. Anthony finished?
15 more seconds.
Okay. No rush, no rush. Just making sure everything is on par. I want to have a nice one with Ellen.
Sir, is the master's program, I don't know how to put it now. Is the master's program going to be manageable? No, that's not what I should have said. Do you think I can manage a master's program? That's what I want to ask.
I don't know because I don't know the full setup for it yet. Because currently, you see, the way I can tell if you can manage it is based on who I know is going to teach. There's certain lecturers that are going to be there, I can say yes or no.
Wow. Okay then.
The topics, I mean, they're manageable, but to be honest with you, I mean, there are some lecturers that I've seen teach courses that are easy and they make it hard. That's why I said that.
But the fact that you are, because I think this is your fourth, third or fourth course now that your fourth course now you're teaching.
Uh,
And I'm asking you based on that basis as one of
you
my
asked me if you can manage it or if you can manage the one at NCU. That's what I mean. That's what I was asking. I thought you were
NCU,
asking specifically about NCU one. Or
NCU
you're
I'm
asking
doing
if
it,
you
but
can manage
I'm not, I'm doing it NCU, but I mean in terms of what you would have seen based on teaching me and say, okay, Jeremy, yeah, you have the
Oh, so you're
capability.
asking about your capabilities, not
Yes.
generally, not necessarily what you're doing. Yeah, man, you can manage it. That's what I'm saying. Because of how you think.
Okay, that's what I'm wondering, sir.
Yeah, man.
Okay, all right, thank you.
Or but you have to brush up on your algebra though. Or you're gonna have some, you might get left behind. So sometimes you think that you're slow, but you're slow because the foundation is not as strong as it should be.
Because I did not do college algebra and the algebra, whatever algebra I've done at high school was pretty much over 20 years ago.
That's why you need to brush up. You see, the higher you get in math, now, the more the basic stuff come up, and they're important. You have to make sure that's strong. Until must finish by now, man.
Okay,
Finish?
sir.
So go ahead.
Okay. Limit. How much minutes we have? 7 minutes? No, that minutes. I thought I had more than that. Limit as x n tends to infinity. Yeah, let's talk with x. X tends n to infinity for exponential function. Normally I would have asked you guys what you think that is, but inches of time is equal to 0. Now as x gets larger, that gets smaller, because remember it's going to be 1 over infinity. A matter of fact, worse than infinity. Of course, that's foolishness, but 1 over e to infinity, that's even more infinite. Because that's like 2 point something raised to infinite power, so it gets, you know what I mean, get big. No, so I want to prove that this is less than epsilon, or any epsilon. I can show that it's getting smaller and smaller and closer to it. Not necessarily equal, but very, very close to it. Which you know to be true, but let us prove it. Let's find a particular m that satisfies that no matter what. So e to the minus x minus 0. Of course, we know that this is equal to e to the minus x, the absolute value. The absolute value of e to the minus x. No. E raised to any number cannot be negative, because remember, e is a positive number. No matter what power you raise it to, it can't be negative. You can't raise a positive number to a negative power, to any power, sorry, and get a negative result. That's impossible. That's why the logarithm of a negative number is undefined. So this is equal to e to the minus x. Simply. Now that, remember, even though it's me equating all of these things, I probably should have started from the start, because I'm doing it that way. I think people understand it better that way. I understand it better that way. We're starting with this statement. Simplify it to this one. We simplify it even further to this, because e to the minus x is already positive. Now, we need to solve for... I was writing foolishness, you know. What did I give you at the start? It should have been e limit as n tends to infinity, or e to the minus n. As I used to x, I'm sorry. It should have been n. As a sequence, as you put in the n values, it gets larger or smaller and smaller and smaller. Sequences normally use n. So if you just change all the x's, please, to n. I'm sorry, I'm not so used to x. All right, that's what I was doing. Pardon about that. E to the minus n minus 0 less than epsilon. E to the minus n is less than epsilon, which breaks down to e to the minus n. I told you why already. It's always positive. It's less than epsilon. To solve for e now, beg your pardon, to solve for n, we take natural logarithm of both sides. ln e to the minus n is less than ln e, epsilon of e. And ln cancels e, so we get negative n is less than ln e. Remember, we're solving for n. So if we multiply both sides by -1, n is less than negative value or negative ln. Oh Lord, it's because I keep saying e is epsilon. So make mistake when you go too fast, you know. ln epsilon. If I can write over this. You guys should know that epsilon. All right, so our x is going to be greater than, our n is going to be greater than negative ln epsilon. Remember that n is going to be a positive number. Oh Lord, I make a big mistake right here. Big mistake. I multiply both sides by -1 and then flip this thing around. I'm writing the next line. N is greater than negative ln epsilon. You might say, but that's a negative number. No. As epsilon gets smaller and smaller and smaller, meaning close to 0, ln of it is getting very large. You can try it if you want. Find the ln of say 0.00000000005 or 0.004 or whatever. You're gonna get a big number. And it keeps getting larger as you go closer and close to 0. And it's negative as well. You get a big negative number. Negative makes it positive. So m is going to be a large number, which is greater than negative ln whatever epsilon we choose. It gets close to 0. So that is the m that we'll be using. So let me know when you finish writing that so I can go to the proof. Or you want to try it yourself or you want to do it? Hello? Want to try it yourself? Next class, let me know if you want me to. But for me to continue, you need to have finished writing. Are you finished writing?
Yes, sir.
Maybe I could squeeze over here. No, never mind. I can finish over here. It's pretty small. So now that we have gotten our m, you remember this first part, you're going to say let epsilon be greater than 0. Always start with that. And choose whatever m you wanted or you found. Choose m to be greater than negative ln epsilon. All right. So we start with it again. E to the minus n minus 0. This time I'm going to work in one line so I can just have space is equal to 1. Of course, remember that n is going to be greater than m or equal to it. So e to the minus epsilon, which is equal to epsilon. I'm getting confused with the e and the epsilon. E to the minus n is coming right here. So guys, watch out for my x's and my n's and my epsilons because I'm mixing them up. Let me go slowly now because I have 1 minute left. E to the minus n, which, remember, we're saying that that is less than epsilon. What we have chosen n to be greater than negative ln epsilon. Reach this yet? So e to the minus n now. So we have so far. So it's equal to. Now, we put in the n right here. Remember that n is greater than what I say, m. So we're going to use the m now. Think about it before I go any further. I want to make sure you understand it. The bigger n gets, what happens to the bigger n? Look at e to the minus n. The bigger n gets, is that thing getting smaller or larger? The bigger n gets. The expression e to the minus n, is it getting smaller or larger as n increases?
Smaller.
Smaller. So if we are saying that e to the minus n, it must be less than e to the negative ln epsilon. What? How you know that, sir? Well, you a while ago just answered me. You said that if n is if n is increasing, then that means that e to the minus n is getting smaller. So we already said that n is greater than negative ln epsilon. If you put a bigger number in there, it's going to be less than it. Make sense? I'm not sure what I'm talking about. I'm talking about these two. This one right here is smaller than this one over here. I mean, greater than it, beg pardon. How do you say smaller? Sorry, the one on the right is bigger than the one on the left. Or is it less than? Less than it. I confuse myself. You're right. N, the one on the line on the left, sorry, we just assume at the top is larger than the one on the right. Which means that e to the negative n will be smaller than e to the negative ln epsilon. Because as I said before, the bigger the number is, the smaller the e to the negative number. So for example, e to the negative 10 is going to be smaller than e to the negative 4, because 10 is bigger than 4. So if n, which is the m that we choose up the top, is greater than a number, then e to the minus n will be less than e to the negative number. Understand what I'm saying? Everybody agree? Understand? I mean,
Yes, sir.
Okay. But so e to the negative n will be less than e cancels ln. So to make it work out, we're going to carry the negative number there to the. I made a mistake again. Oh boy. Scratch this line right here. Scratch this line. E to negative n is less than e to the negative ln epsilon. Replacing the n. So negative epsilon. Negative, because remember m is greater than negative ln e. There was already a negative there. So we need to take account of that. So e to the minus n is less than e to the ln e epsilon. Ln cancel e, so we're getting e to the negative n is less than epsilon. So we have now shown that if m is greater than negative ln epsilon, then this thing from the start, which broke down to this thing right here, is less than epsilon, which is what we wanted to prove. I wish I'd use a different slide because you want me to work it over? Because I don't want it to get confused with the mix up over it right here. You understand it?
I'm gonna review it for next class because you have like 6 minutes remaining.
No, man, time up. It's just that because of everything I did right here, if you follow the things I didn't mark out, if you follow from the first part to the next one to the e to the minus n right here, and you jump to this line right here, it should be right. But I didn't read the flow because I had to cross out some stuff.
Yeah, man. So and then you're gonna finish. You can finish it up from there, right?
That's it. You have proven that it's less than epsilon. Once you prove it's less than epsilon with the m that you choose, then you're good.
QED.
Proven.
Okay.
Yeah. So the whole purpose of this is to find an m that will make the statement that I underline right here true.
You don't make a statement when you reach down to that bottom line. You don't say nothing at all. It's a QED or something.
Yeah, we normally say QED. Write a little box. The little box means QED. I think there's three things you can write. You can write proven, QED, or that little box. I didn't draw the box properly. It's supposed to look like more like this. Yeah. But that means proven.
A rectangular box.
Little box. When I went abroad, well, that's not true. I learned at UE. When I went abroad, I saw them use it all the time. The lecturers. Mathematicians are lazy people, even though it's for proof stuff and what we're trying to find all shortcuts to make it simpler. They move from proven, QED, to box. I don't know who came up with the box.
Okay.
Because I know QED means proven. The box now that's lazy. So once you show that the absolute value of the limit, the sequence minus the limit is less than epsilon, you have proven what you wanted to prove. And to get to that, you need to find the m that will satisfy it. Because you're going to always put that m back in the proof. This is very similar to induction, you know. You find the thing and then use that thing to prove the next part. But it's actually backwards. You go backwards and find the m, then you go back and put it in there so that no matter what, you can use that m. That m will satisfy any epsilon that you pick. So I'm hoping with all these examples it makes it a little clearer. If we're going to come to the next class, I'll probably do one more and then we'll move on. I'll be asking for your input. So revise these, review them, understand it. Because next class I'm not using next, I'm going to be asking for your input. What do you think we should do next? What next? So I'll be testing to see if you understand it before I give you the actual test. Anyway, any questions?
No, sir.
Stop in here.